there's a lot of conclusions that are drawn in the medical literature that are simply unwarranted. So, if, for example, we have a look at the Sydney Diet Heart Study or the Minnesota Coronary Experiment, which are both from the late 60s, early 70s, they actually found that removing saturated fat from the diet and replacing it with polyunsaturated seed oils was actually deleterious to health. And yet, for reasons only known to the investigators, and I think we can actually paraphrase a little bit here, because one of the investigators of one of these studies was actually asked before he died in an interview how they published the results. And the simple fact is they delayed publication significantly. And even when they originally published, I think the Minnesota Coronary Experiment was published 16 years later after the conclusion of the study, they didn't provide data on all-cause mortality. And the study investigator simply said, we didn't like the results we got, so we didn't publish. The Sydney Diet Heart Study, they never published the all-cause mortality data either. And the only reason we actually know the results of these studies today is because somebody went and dug out the results from old basements. They actually discovered them, decoded them, used reinterpreted all the results according to good scientific methodology. And lo and behold, we have the results. Large-scale randomized control trials show that eliminating saturated fat from the diet in place of polyunsaturated fats, that is, reducing your saturated fats, actually increased mortality. And we would never know this. This was good quality science that was destined to be lost to history. The Women's Health Initiative is another example, a little bit more surprising because it's in the modern era. They actually had a largest randomized controlled trial in the world, $700 million US, and they had a group of females who went on a low saturated fat diet. And the only statistically significant finding from the whole study was a 26% increased risk of complications such as angina and heart attacks and so on and so forth. And given that that was the only finding of the whole study, you would think it would be front and center of the results, front and center of the conclusion, mentioned in every press conference. Well, strike out on all three accounts. It wasn't in the results table. It wasn't in the conclusion. It was never mentioned in any of the press conferences. It was written in obscure language on page 661 of the reporting journal. This is just absolutely amazing. We have solid science and it's literally buried. And we have plenty of other examples of this going on. We have misinterpretation of bad science. So in 2020, I came across a paper that studied cholesterol supplementation and atorvastatin, which is a statin, a cholesterol-lowering medication use, in New Zealand white rabbits. Clearly, has no applicability at all for humans. And yet, in the conclusion, the authors of this paper suggested their results did apply to human patients. This is 2020, and we're using rabbit data to inform our use of statins. There was another study that actually looked at statin use, and it found that it actually increased the incidence of diabetes. So if I actually can quote, they said that it was a New England journal, actually this is a few years old, 2008, it was a statin trial. They found that there was a significant increase in physician-reported incidence of diabetes, and there was a statistically significant increase in HbA1c, which is a marker of average blood glucose levels. The authors also acknowledged that prior to this time, there were independent studies that confirmed worsening sugar control for at least 3 different types of statin medication. So on the basis of this, they had statistically significant findings. Now, my understanding, and everybody's understanding of statistical significance, is that it represents findings that are unlikely to be due to chance. We want to take out the element of chance, and we do that to a reasonable degree. Still, in the conclusion, these authors said, well, this worsening sugar control could reflect the play of chance. That defies the logic of having statistically significant findings. They simply could not compel themselves to look at the science and understand the science and say, oh, maybe statins are bad for diabetes. Maybe this is the evidence. Nope, they just said, oh, look, it's probably a random chance. Never mind that it reached statistical significance. There's a problem where we have something called eminence-based medicine, and that's totally contrary to evidence-based medicine. Evidence-based medicine means we look at the data, we draw a conclusion. Eminence-based medicine means that we put our trust in other people, not the data. We actually allow eminent people, experts, if you will, to provide us with their conclusion because they're clearly smarter than we, and we can accept at face value everything they say. So there was a paper from the American Diabetes Association, which is very, very heavily cited, and it's on the use of statins in diabetes. And I had a lot of people tweeting this paper at me and emailing me this paper and saying, see, this proves that statins are good in diabetes. I went and looked at the references. There were 6 references on this paper. 3 of the references did not include all-cause mortality as a measure of outcome. That is, they didn't actually ask the question, let alone answer the question, whether taking statins for diabetes, patients with diabetes made them live longer. The 3 studies that they included that did actually ask the question about all-cause mortality, they all had insignificant findings. Not one of the references in this paper showed what they said it did. And yet, this is a very heavily cited position statement from an expert body that recommends the use of statins in diabetes. And this is just madness. And if people actually understood that the wool was literally being pulled over their eyes, you can't trust the conclusion, you can't trust these guidelines, you can't trust these expert bodies. You have to look at the raw data. When you look at the raw data, the truth is very, very different. I don't think there's any ulterior motives on the side of doctors who are making these conclusions. I think it just comes down to pride and intellectual arrogance. They're used to being the smartest people in the room, and they really don't want to concede that they could be wrong about anything. And I mean, I can speak to this from personal experience because I haven't always been an advocate of low seed oil, low carbohydrate, ketogenic style diets. I used to be, lock, stock and barrel straight down the line, making these recommendations that people eat low fats on and so forth. And I was absolutely adamant in that. And the position I was coming from was supreme confidence that I'd had an academic education and therefore I was right. I just hadn't even considered the possibility that I was wrong because I trusted the people who had taught me. I get excited when I read a research paper where they actually find against their original hypothesis and they report it clearly as such. There was a paper from the American Journal of Cardiology in 2004, and they predicted that saturated fat would increase LDL oxidation. So just to make very clear, LDL, low-density lipoprotein, which is often pejoratively and incorrectly referred to as bad cholesterol. So LDL in and of itself is not harmful, but if that LDL becomes damaged, and one of the ways it becomes damaged is through oxidation, then it can contribute to what we call the atherosclerotic burden or plaque, basically lining your blood vessels. So this paper predicted that if people had more saturated fat, they would have higher oxidation levels of LDL. And in actual fact, they found that it was polyunsaturated fats or vegetable and seed oils that did this. And in their conclusion, they stated, these experiments provide convincing evidence that our original hypothesis was not correct. Clear, unambiguous language. And I think that is just fantastic science. That is how science should happen. Just on the 25th of February this year, 2021, there was a Cochrane systematic review published on vegan diets and cardiovascular risk parameters. Interestingly enough, they looked at all the randomized controlled trials that had been done on vegan diets, and not one of those trials not one randomized controlled trial available for this systematic review actually looked at clinical outcomes. What that means is it didn't actually look at things that actually matter to patients. It didn't look to see whether they had shortness of breath or they had impaired cognition or how they're, whether they had more heart attacks or these kind of things. So the only thing we can rely on for this research is surrogate markers. Surrogate marker means we see something like a blood test moving in a certain direction, and we would assume that that's bad because our experience is that, high triglycerides, for instance, is not a good sign. That a lowering of your HDL, good cholesterol, is not a good sign. And this systematic review actually found that HDL cholesterol went down on vegan diets and that triglycerides increased. And they actually acknowledged that these changes in the lipids were opposite to what they had predicted. Now, funnily enough, I suspect they meant to write opposite to what they'd actually hoped for. But either way, they actually did acknowledge that the changes of these direction, and certainly suggesting that they're actually not good for health. So I think the state of affairs is, as of the 25th of February 2021, the best evidence we have for vegan diets on health appears to be deleterious. The LDL change, the LDL actually also went down on a vegan diet. And it depends on your worldview of LDL. If you subscribe to the old debunked theory that LDL is a bad thing, then you can say, well, maybe these changes in HDL and triglycerides are offset by the change in LDL. But the simple fact is a lowering of LDL is almost certainly associated with an increase in cardiovascular risk. So, and we've got meta-analysis and systematic level of data proving that. If I give you an example of one study, so it was done by Bathum, Bathum, in 2013, and they had a touch over 118,000 subjects who were all over age 50. And what they actually found that the people with the highest level of LDL had on average about a 50% reduced chance of dying than the group of people with the lowest LDL. So you can flip that the other way and say that if you have the lowest level of LDL, your risk of dying is doubled. Well, these people were aged over 50. So there's still a lot of life left in at age 50. They also excluded people with diagnosed heart problems and cholesterol problems who had been prescribed statin medication. That excluded people with cardiovascular disease. They excluded people with diabetes. They excluded people with any hint of terminal disease at all. So for all intents and purposes, this was a healthy, younger population. And they found that the lowest LDL level increased your all-cause mortality by about double compared to having the highest all-cause mortality. LDL serves an important function in our body. If we had no LDL, we would simply die. Full stop. However, LDL can be damaged. And if the LDL becomes damaged, then we have a problem. And because what actually happens is that normally our LDL has a lifespan. Our liver excretes something called a lipoprotein. It's called a very low density lipoprotein. As that very low density lipoprotein, it's like a big boat and it's got triglycerides and cholesterol inside. So cholesterol is just a molecule. Cholesterol doesn't actually mean LDL. LDL is so much more complex than cholesterol. It's what we call a lipoprotein. It's a complex structure, but it carries some cholesterol inside. So this term to call LDL cholesterol is just frankly wrong. Otherwise, if a passenger was riding on a bus, you don't call the bus the passenger. The bus is the bus. The passenger is just what's inside. So this VLDL molecule gets released from the liver and it gives cholesterol to tissues around the body that need it. It gives triglycerides to where it needs to be for energy or for storage. And as it does so, it shrinks. And as it shrinks a little bit, it gets an arbitrary name change to intermediate density lipoprotein. And then as it donates a bit more of a cargo, it shrinks again. It's like a deflating balloon. Same particle, it just now has a different name, arbitrarily different name. And after it goes from intermediate density lipoprotein, it becomes a low density lipoprotein. And then this low density lipoprotein can be taken back up by the liver, and the cycle continues. And this is important for life. And it's also got immune functioning roles and a bunch of other stuff. Now, if the LDL is damaged, the pathway by which the liver takes it back up out of circulation stops working. Basically, you've got one molecule on the outside of the LDL molecule or the particle that identifies it. It's called an ApoB100. That's its security swipe card. And if you damage that security swipe card, then you can't get taken out of the blood by the liver, and then you start to accumulate. And one of the things that can damage this ApoB100 security swipe card is oxidative stress. So we actually know that it's oxidative stress that turns LDL bad. And if LDL is damaged, then it can accumulate inside the internal wall of the blood vessels. It actually looks like if you've got a long blood vessel going down, you've got little small blood vessels coming in from the outside. They're called vasa vasorum. It's basically a tiny blood supply to the big blood vessel. And these LDL particles actually travel through these small blood vessels, and they can lodge into the middle of the wall, what we call the intima, and that's where these fatty deposits form. But if your LDL is not oxidized, that process doesn't occur. And the interesting thing is that a high triglyceride level and a low HDL level are really just markers of oxidative stress. That's a simple way to think about them. So if we just think about, damaged LDL is what causes the deposition. And if you have a high triglyceride level and a low HDL level, then you're much more likely to have damaged LDL particles. And it really is that simple. And this is well supported by evidence too. So everybody's worried that once you've got these fat deposits in the blood vessel wall, well, they must be there forever. Well, that's not true. We know that what we call plaque regression is possible. And in observational studies on plaque regression, they actually found that some people were able to get their plaques would actually disappear, or they would actually shrink over time. And some people, their plaques would actually get worse. They would actually increase or progress. And what they found was that those people who had plaque progression, on average, had LDL levels about 50% of those people who had plaque regression. Think about that for a second. We've actually got documented evidence in observational studies that it's possible to reverse these atherosclerotic plaques. And the people with the highest LDL levels are the ones who get reversal. The people with lower LDL levels actually have progression. And I don't know about you, but just that single observation should be enough to debunk this whole LDL myth that all LDL is bad. Yes, LDL can be bad, but only if it's oxidized. If you're otherwise metabolically healthy and it's not oxidized and it's not damaged, then you're going to be okay for the most part. Now, there are some things that we know that increase oxidative stress, and that's seed oils and too much sugar or too much carbohydrates. So we know that when the blood sugar levels are going up and down, we've got very good evidence that generates oxidative stress. That generates these reactive oxygen species, or these electrons with an unbalanced valence shell electron that can actually damage other tissues. So you don't want your sugar to be going up and down every other moment. And the other thing is seed oils, by definition, they've got bonds that are prone to oxidation. And when you consume them, these oxidation products actually literally get taken up by these other particles called chylomicrons and get delivered to the liver. And we've got evidence, we can see this on electron microscopy, where these oxidized particles actually lead to damage of the liver, insulin resistance, and they actually then, through a whole series of downstream events, lead to your triglycerides going up and your HDL going down. So if you're worried about your LDL level, don't worry about saturated fat, because saturated fat will make your LDL go high. Sure, it can do that, but it won't make it go bad. What will make your LDL go bad is having very unstable glucose levels and consuming a lot of oxidized seed oil. You can actually measure LDL directly. And that's very easy. So when the LDL gets oxidized, these little surface proteins actually denature, they actually shrink, they change their structure. So if you damage an LDL particle, there's a tiny, tiny fractional shrinkage of it. And this is what we call small dense LDL. I'm sure you've heard the term. Now, this is actually a terrible term because we have people talking about these large, fluffy molecules and small dense particles as if there's a significant size difference between them. It's infinitesimally small. It's a tiny size difference, but it is measurable. We can actually measure it. Japanese scientists way back in the 90s, they've actually figured out that when you actually have sugar binding to the LDL particle, it denatures these proteins and lead to a shrinkage. We've actually got evidence that glycation damage as well as oxidation damage leads to small dense LDL. Now, we can put a sample of your LDL into a gel and we can either centrifuge it, so spin it down, or we can apply a current through it, so-called lipid electrophoresis. And both of those measures reliably separate out the LDL based on the density, the size of it. And we can actually then see how many different LDL populations you have. Normally, you should only have one smooth peak, and that's basically healthy LDL, physiological LDL. That's not going to harm you. Not in 100 years. That's good LDL. But if you start having it damaged, then you'll see more peaks. So the first step is you'll get a second peak. And my clinical experience is that when I correlate people with 2 peaks with something called a coronary artery calcium score, which is a direct measure of calcification inside the vessels that correlates very tightly with heart disease, that having a second peak doesn't seem to be overly problematic, but it's obviously not ideal. But once you start getting 3 peaks or 4 peaks or 5 peaks, then all bets are off. Then we start seeing significant atherosclerotic burden. If we have a look at triglyceride and HDL, though, we know there's this association with oxidative stress. And we've got very reliable associational data. It's not as good as directly measuring it, but we can infer with a high degree of reliability whether somebody has good or bad LDL simply by having a look at the ratio. And we do something called a triglyceride to HDL ratio. We divide the triglycerides by the amount of HDL. And I've actually got a couple of lectures online where I talk about this and talk about what thresholds are generally associated with what we call a pattern A LDL pattern or a non-oxidized LDL. If you are metabolically healthy, you can undergo an oral glucose tolerance test with almost zero deviation of your sugar supply. So to talk about people who are metabolically healthy with extreme glycemic variability is an oxymoron. People who are metabolically healthy don't tend to have that degree of glycemic instability, full stop. So I actually, when we debate about whether it's possible to reverse type 2 diabetes and people say it's only being controlled on a healthy diet, it's not actually being reversed. No, that's not true. I've actually done hundreds of glucose tolerance tests with insulin, otherwise more commonly known as the Kraft test. And I've got multiple patients who have actually been able to restore flat glycemic control in response to a 75-gram load of glucose. Now, number 2, we actually have solid evidence from the mitochondrial level that there is oxidative stress that is generated when glucose is a source of fuel. And the greater the flux of glucose, the greater the oxidative stress. We've got ground level, almost molecular level data confirming that. And then we have experimental data that also shows that. So we actually know that vegetable oils are oxidized. And when you consume them, you actually have these circulating oxidized molecules in the blood that we can measure. We can actually measure the oxidative load after somebody consumes a load of vegetable oil. And then they did a very nice study. They got subjects who were either insulin sensitive, which means their insulin levels worked well and their glucose levels were well controlled, or insulin resistance, which means that their sugar levels were going up and down. And then they gave them the same load of oxidative stress. And they found that there was a huge increase in both the amplitude of oxidative stress in those people who are insulin resistant that persisted for well over 24 hours after one meal of seed oils, oxidized seed oils. And for anybody who's thinking, oh, that's good, I don't have any oxidized seed oils, by definition, if you're having a seed oil, it is oxidized. There's no other way for it. And olive oil doesn't escape either. The reason that these oils oxidized is because they've got these unsaturated bonds. The only difference between a polyunsaturated oil and oleic acid, which forms 70% of olive oil, is that there's only a single bond prone to oxidation in olive oil, whereas there's multiple of them in seed oils. So olive oil is too prone to oxidation, just to a lesser extent by virtue of having less of these bonds. Saturated fats, by definition, they don't have any of these bonds that are prone to oxidation. So there is absolute clear evidence that this glycemic instability from a mechanism and from subjects who actually are insulin resistant with poorer sugar control, that actually does lead to these much higher levels of oxidative stress. And if you've got these oxidative molecules circulating around your body, have no doubt that they're reacting with some of your liver tissue. They're contributing to worsening your insulin resistance. Again, it's a vicious cycle, as well as potentially interacting with LDL molecules in your blood and damaging them. And we need removal of commercial interest from our food guidelines. People are under the misconception that the dietary guidelines are formulated based on food that's healthy. And that simply is not the fact. There's a whole lot of other commercial interests and lobbying interests that feed into that, including the food that's currently available, the food supply that, if everybody overnight went on a healthy diet, there would be food shortages because there's simply not enough healthy food around. So all of these kind of interests actually play into the advice that the governments around the world give their populations on what to eat. So people should not be under the misconception that the dietary guidelines are what is healthy, because they're not. They're absolutely not. And if you read the fine print, they say, well, these guidelines apply to people that are healthy. So if we take the American population, there was a national survey that found that based on 5 markers of metabolic health, only 12% of US adults are healthy. Think about that, 12%. So by definition, the dietary guidelines in America only apply to 12% of the population. There's something else even more important that we as humanity are slumbering into, and that's the environmental destruction of topsoil. The problem with agriculture is that every time you take a plow to soil, you expose trillions of bacteria to the sun, to the wind. We basically denude the soil. There's no surer way to turn soil into dirt than to plow it. And unfortunately, this is a finite resource. Ruminant-based agriculture can actually regenerate soil, while plowing it actually denudes it. And we are going to reach a point where topsoil is completely denuded and we can no longer produce food. If we have no topsoil, it doesn't matter if you're a vegan or a carnivore, there is no food. Now, if you have grazing ruminant animals, they will actually feed on the grass. So the grass is converting energy from the sun, photosynthesis, into cellulose and providing nutrition. The cow's eating the grass. The cow is then fertilizing it with manure and also with water, with urine. So when people talk about the amount of water that a cow drinks as it being waste, that's completely and utterly illogical because it doesn't stay in the cow. It actually then irrigates the field that they're on. Some of the grass that they're eating, the root system dies, and that also contributes to the biomass of soil. And over time, the thickness of soil will actually grow. This is what ruminants do. They actually grow soil. Whereas when you take a plow to it, you destroy soil. And this is actually a real cause of concern for me because it might not be in our lifetimes, but it's not that far away. I suspect we're going to start seeing problems of the soil being denuded, at least in the next generation. Well, we've actually got studies in Australia, so comparing from 1950 to about 1990, and they're actually measured crops grown across all nutrients, and some nutrients were down 75%. Literally a quarter of the degree of nutrition in crops now as what they used to be. And this was published in the 1990s, so 30 years ago. But it's going to be far, far worse by now. The problem is that food actually takes nutrition out of soil. And you don't actually need to replace all the nutrition back into the soil to have a crop necessarily grow. It needs certain nutrients, sure. So it might be deficient in nutrition, but it still looks good, it still grows, it's still green. And this nutrient deficiency is absolutely a huge problem. And that's going to affect everybody. And fortunately, with ruminant-based agriculture, then that's not depleting the nutrition status of soil. But if you're growing crops, it absolutely does that. Absolutely huge, because these micronutrients do actually matter. They matter a lot. So if we take one, which is copper, we know that copper has a very important balancing role in terms of oxidative stress that can be caused by iron. Iron is a very reactive molecule. It's essential for good health. But if you have not enough copper, then the iron you have can actually become very pro-oxidant. And we see this in a condition called hemochromatosis. So hemochromatosis is a condition where you will genetically just absorb more iron from your diet than you normally would. Now, we used to think about this, and indeed most people still do think about it as an iron overload condition. But it's not so much an iron overload condition as a nutrient imbalance, because when you're absorbing extra iron coming in through these certain transporters, they have a finite capacity. And that means that you're displacing the ability to absorb other nutrients such as zinc and copper, which share the same transporter. So it's not so much an excess in iron that's causing the oxidative damage and the deleterious outcomes we see in hemochromatosis, but a relative deficiency of these other nutrients like copper and zinc, which actually have a role in stabilizing the iron molecules. So these micronutrients actually have a hugely important role. And the fact is that when we actually look at the cardiometabolic health of people with hemochromatosis, it's often far, far worse than average. We often see extremely high levels of triglycerides.